is sort of a minimal categorical setting for differential geometry. Synthetic differential geometry is one of the first sort of ways of exploring differential geometry via category theory. In some sense, that's the nicest setting for differential geometry. It's really taking the ideas of a lot of the original differential geometers and making them precise in a nice categorical way. Tangent categories are sort of a different approach where we're looking sort of what is the smallest categorical structure we could have so that our categories could do differential geometry. And what's interesting about them, they start to span a wide variety of examples. I'll talk about some examples in a minute after I give the definition. They span a whole wide variety of examples from differential geometry. There's been different categories. The canonical categories are the category of smooth manifolds, but there's another sort of variants of those categories, which are usually tangent categories as well. In algebraic geometry, there's kind of tangent bundle type constructions. These give tangent categories. And some recent work, which Christine Bauer will actually talk about in the session later today, is how some ideas in abstract homotopy theory about functor calculus can also be seen as tangent categories as well. So in addition to there, be lots of examples of them, many structures can be defined in a tangent category. So if the claim is that they're a minimal categorical setting for differential geometry, you really have to show that by showing that a lot of the structures that you deal with in differential geometry can be defined in these categories. And that's part of what myself and some others are working on in the last few years is showing that in this abstract setting, many things can be defined, such as analogs of vector bundles or differential forms, connections, all sorts of things. Really, the goal overall is to be able to open up sort of a standard differential geometry book, sort of flip to a random page and be able to find an analog for that in tangent categories. And so as part of that program, what I want to talk about today is how we could think about the cotangent bundle in tangent categories. So in general, a tangent category may not have a cotangent bundle, but we'll talk about structure we could add to a tangent category, which would give it a cotangent bundle. And so the plan overall is to review tangent categories, what's their definition, and particularly talk about differential bundles, which is the analog of vector bundles in a tangent category. I'm going to talk about linear dualization, what that means for a tangent category, and how if I have this, it gives a cotangent bundle in a tangent category. And sort of the question at the end, and what the title refers to, is can we axiomatically define a cotangent category? So axiomatically, a tangent category is some category equipped with some abstract tangent bundle. In some places, some differential geometry texts and algebraic geometry, the cotangent bundle is seen as more primitive, more basic than the tangent bundle. And so part of the question is, could we directly axiomatize a category equipped with a cotangent bundle as opposed to a category equipped with a tangent bundle? And so far, not sure the answer to that yet, but hoping some of these ideas I'm talking about today will lead towards that. Okay, so let me just start off by giving the definition of a tangent category. So again, it's sort of abstracting the structure of the tangent bundle functor on the category of smooth manifolds. And it was originally due to Rositsky in 1984. Robin Cockett and I sort of rediscovered it and generalized the idea a little bit in 2014. So a tangent category is some category, and first of all, it has an endofunctor, a functor from the category to itself. And you're thinking of this as representing, given some kind of object in the category, its tangent bundle. So again, the standard category is the category of smooth manifolds, and so spaces that smoothly locally look like Rn, spheres, toruses, things like that. And its tangent bundle is taking all the different tangent vectors at different points in the space and taking them all together and assembling a new smooth manifold out of that. And that action is actually functorial as well. If I have a map from M to N, that I get a smooth map from the tangent bundle of M to the tangent bundle of N. So locally, it's given by the directional derivative. So what other structure, part of the question is what other structure does this endofunctor have? So it turns out to have a bunch of natural transformations as well. So at every point of the tangent bundle, it's a tangent vector. Every element of the tangent bundle is a tangent vector at a point. So pulling off that point gives us a natural transformation from the tangent bundle Tm back to M. So a natural transformation from T to the identity functor on X. Now I have to be a little bit careful about pullbacks. Category of smooth manifolds doesn't have all pullbacks. Lots of places, lots of things which don't have the pullback to max doesn't exist, but there are certain pullbacks which do exist. And so we'll ask, for example, that the pullback of n copies of Tm over M along itself exist, and those preserved by all the sort of iterates of the tangent bundle. And you can think of this space T sub nm, this pullback, as a space of n tangent vectors at a given point. Now, given two tangent vectors at the same point, you're supposed to be able to add them. So we can say that by asking that this have the structure of a commutative monoid in the slice category. And that gives you operations plus going from T2 to T, taking two tangent vectors and adding them, or the zero operation taking a point and giving you the zero tangent vector at that point. Notice that we're not asking for subtraction of tangent vectors. That turns out to be useful in some examples to not demand that you can also subtract tangent vectors. So we're not asking for that in the definition. So that's part of the structure, and the rest of the structure is here, well, the basic ideas. So it turns out that when you take the tangent bundle of the tangent bundle, which is sort of quite hard to visualize actually. Already the tangent bundle itself is kind of hard to visualize as a structure in its own right. And imagine taking that and taking the tangent bundle of that again. But it turns out there's a natural transformation from t squared to itself, not the identity, but when you do it twice, you get the identity, so it's involution. And this is something you see occasionally in differential geometry places, but it sort of becomes a central structure in the way we're axiomatizing things here. And one thing that's nice about it is if you sort of work out, so this natural transformation just sort of, in a sense, kind of flips two interior coordinates. And the naturality turns out to be, when you look at it in smooth manifolds, the naturality of this is saying the symmetry of mixed partial derivatives at d squared f dx dy is d squared f dy dx. So that's a very natural thing. That sort of gives you that symmetry of mixed partial derivatives in a sort of categorical way. There's also natural transformation from t to t squared, so taking a first order tangent vector and giving a second order tangent vector. And really part of the usefulness of that appears in this pullback diagram here. So one of the sort of key axioms of a tangent category is this pullback diagram here. And it's sort of hard to understand a little bit at first, but essentially what it's saying, what it really is saying in sort of a bundle type way, is that each of the tangent spaces themselves have trivial tangent bundle. So think about the tangent bundle. It consists of all these tangent vectors, all different points. And you can look at the tangent vectors sitting over a fixed point. And in the ordinary case, that's a vector space. And notice that we don't have any kind of real number object here. There's no assumption of anything like that. So we can't ask that those tangent spaces be vector spaces in the traditional sense. But another sort of important property of vector spaces and think about their tangent bundle is that their tangent bundle is trivial. The tangent bundle of vector space phi is isomorphic to v cross phi. So this property here is essentially representing that this property here is kind of saying in a bundle type way that the tangent bundle of each of the tangent spaces are trivial. So the tangent bundle of each of the tangent spaces are like v cross phi. I see that coming out here, that essentially certain elements of t squared are represented by a pair of first order tangent vectors. So I could talk more about that, but it sort of would take a while to sort of discuss that a little more, but that's the idea of what that pullback axiom is saying. Okay, so give another examples of here. So the canonical example is smooth manifolds, their tangent bundle. You can go to infinite dimensional settings as well. So convenient manifolds were developed as a sort of setting for infinite dimensional differential geometry. There's something called the kinematic tangent bundle that form the tangent category. If we go to synthetic differential geometry and focus on sort of the nice objects there, that gives a tangent category. Category C infinity rings has been proposed as another sort of nice setting for differential geometry. That's a tangent category as well. A lot of categories in algebraic geometry that people use, commutative rigs or rings, so rings that negative rings. They're opposite categories, schemes, those are tangent categories as well. One example is sort of floating around, and Ben McPadam recently sort of actually worked through the details and showed this, is that a very interesting example, you take the category of all small categories with finite limits, store all possible small categories with finite limits, and if you define T of a category, so the tangent bundle of a category to be the category of Beck modules in X or the abelian group objects in X, that turns out to form a tangent category as well. It's a very interesting, sort of very different example that doesn't, on the face of it, look like differential geometry. Sort of related to this is the Goodwillie functor calculus. This is sort of a one category version in some sense, the Goodwillie functor calculus. And abelian functor calculus gives a tangent category, and Goodwillie functor calculus gives an infinity tangent category. And if you're interested about this, as I said, Christine Bauer will be talking about this more later this afternoon. There's lots of things you can do to a tangent category and get a new tangent category. And so I put one example here. Any tangent category, you can talk about what vector fields are. And if you take the collection of all vector fields, that turns out to form a tangent category as well. And you can do this about a number of constructions as well. You can talk about objects hook up to the connection, and those form tangent categories as well. So that's one nice thing about the definition, surprisingly flexible, and that a lot of constructions you can do, again, give you tangent categories. Okay, so as I mentioned before, there's a number of structures you can define in any tangent category. And one thing we'll need for the rest of the talk is what the analog of vector bundles are. And how do we define vector bundles in a tangent category? And again, there's no assumption of any kind of real number object. So again, we sort of define it by something, a sort of fibered object object QE over M, such that each fiber has trivial tangent bundle. And again, it's expressed by this kind of pullback property. And if you look at what a differential bundle over 1 has, it's sort of one thing with just a single fiber, then you can prove that a differential bundle over 1 is essentially asking that its tangent bundle is isomorphic to E cross E. So again, we can express vector type axioms by directly sort of asking about something about their tangent bundle. And this is sort of how we can phrase it for a general bundle to be a differential bundle. This map here, by the way, this sort of map here, which also we saw in the tangent structure before, kind of lifting of a bundle thing to T of it. The way you can think about this, especially in the case of differential bundle over 1, like a vector space, it's like if you have a vector space and you have a point in a vector space, you can draw a tangent vector from the 0 point to that point. And so in a sense, from a point in a vector space, you can make a tangent vector out of it at 0. That's what this operation in a sense is doing. And it's like kind of like this way of defining, sort of, in a sense, it's an alternate way of defining vector bundles that can be applied in any differential, any tangent category. And Ben McAdam again asserted something else really important, that these really are exactly the same as vector bundles. And there's something non-trivial about that as well, because vector bundles have a sort of local triviality condition, some kind of topological condition. And that kind of sort of comes for free out of this definition, something we hadn't realized when we originally defined this thing. But it turns out you can get that these really are the same as vector bundles by just asking for sort of some algebraic structure in this pullback structure here. It's a nice way of characterizing vector bundles in a very different way. Okay, we can talk about linear morphisms between them. So I've got two vector bundles, sorry, differential bundles, E Q over M, E prime, Q prime over M prime. So a morphism between them would be sort of the natural thing. So first of all, it's a map in the arrow category. So it's a pair of maps which make this diagram commute. But then we ask that it preserve this special lambda map here, this kind of lift thing. And this is nice as well, because this turns out to be equivalent to, in the case of smooth manifolds, asking that it be linear in the ordinary sense. So it's very natural to ask that it preserve this lambda map, but that turns out to be equivalent to being linear in the ordinary sense. If we make some additional pullback assumptions, the pullback of a differential bundle along a map is another differential bundle, then this gives a fibration over the base category. And the T itself can be sort of seen as a functor then going from the base category to this category of differential bundles. That's, in a sense, what these two parts of the axiom are saying, is that tangent bundle of an object is itself one of these differential bundles. Let's check the time. Cool. Okay, so how can we talk about the cotangent bundle in a tangent category? Remember the cotangent bundle, what is it in the ordinary case? It's defined by taking the dual of each of the tangent spaces of M. So you have your tangent bundle, which is all the different tangent spaces at all different points, and you take the dual of each of those vector spaces. So how can we sort of talk about this categorically? One thing to realize is that tangent bundle is not an endofunctor on the category of smooth manifolds. Sometimes you'll see in some places which will sort of talk about functors and natural transformations for a differential geometry that they'll sort of talk about being endofunctor, but if you read this fine print, they're talking about it being an endofunctor when you're strict to the étal maps, the local diffeomorphisms, but it's not an endofunctor in general. What's going on? It really is actually giving a functor a different category, the dual of the fibration of differential and vector bundles. So rather than being an endofunctor on the base category, we'll have to see it as some kind of functor to the dual of this differential vector bundle fibration. So I need to talk about what the dual thing is. So anytime you have a fibration, and it could be like this fibration of differential bundles, but actually just any fibration in general, I think this is sort of an idea that isn't super well known, is that you can take there's an associated dual fibration. So a fibration, sort of in the index category point of view, for each object of B, you're getting some associated category. And in that point of view, you're just taking the opposite category in each fiber. There's a way you can sort of talk about it directly without talking about the index category point of view. I'll give a reference to that later. But it's sort of a nice construction. Again, it's not taking the opposite category of either the total category or the base category. It's taking the opposite of each fiber. And for a simple example of this, let's consider the simple fibration over Cartesian category. So it has objects pairs, objects in original category, and maps are a pair of maps. And the first map goes from A to B. The second map goes from A cross A prime to B prime. So taking in both these things and giving you a map to B prime. So that's a simple fibration. That's a nice example of fibration over a base Cartesian category. What happens when you take this dual construction? Again, you're sort of taking just the opposite in each fiber. So what happens is you kind of flip the role of the A prime and the B prime. So the dual fibration has the same objects, and again, maps will be pairs of maps, and the F goes as before from A to B. So we're not doing the opposite in the base category, but we take the dual in each fiber, which gives us that the F star has to go from A cross B prime to A prime. So these are, I think this is a fascinating category. So I've been talking about this a lot in a lot of talks I've been mentioning. I sort of want to get the word out about this kind of fibration idea, the dual fibration and the dual of the simple fibration, as we'll see the dual of the codomain fibration. They're really interesting categories, I think, because they have kind of a bidirectional nature. They have pairs of maps with one map going forward, so it goes from A to B, but the second map kind of having a forward and backward nature to it, where it takes in an object from A and an object from B prime, something from the codomain, and giving you something back in the domain. And these are appearing lots in, well, they already have appeared lots in sort of various applications, sometimes called the category of lenses. And they've applied in many places, so they're useful in database theory. Functional programming uses lenses. Valeria had this category, just dialectica categories, which relates to ideas of Gödel. They kind of show up there. People using these ideas in machine supervised learning, really because it's sort of operation which is has both a forwards and backwards nature, a bit like learning. When you perform some action, you're sort of going forward, you're told you're doing something wrong, you need to modify something, so you go back and update your assumptions. So learning in a sense has a kind of bidirectional nature like this. And so this category is being used for those kind of applications. So more specifically for us, we want to look at the dual of the codomain fibration, of which the linear thing is a subfibration. So remember the codomain fibration of the arrow category has just objects maps like this, and arrows computing squares. And when you take the dual fibration of that, again, you kind of got a bidirectional nature. So it'll be a pair of a map in the dual fibration from Q to Q prime will be a map in the forward thing from the M primes, but then a kind of backwards thing as well. Something that takes an E prime and an M, sort of fibered over M prime, and gives us something in E. So again, it's giving something both in the domain and the codomain, and giving you some back and something in the domain. By the way, there is, it's not completely directly obvious that such maps compose, but they do from the general theory, and you can sort of figure out how the composition will work. It's kind of an interesting thing to look at. So this particular thing is sometimes called the category of dependent lenses, kind of the dependent bundle version of this one here. But again, it has this bidirectional nature. So the dual of linear fibration is the same as above, except now these objects have to be differential, or in this case of smooth manifolds, vector bundles. And then we kind of got this maps going both forwards and backwards. Okay, so now we come to our first sort of definition, new definition setting. So if we have a tangent category, we can ask to have a functor from the differential bundles to the dual of the differential bundles. And that we'll think of as taking the dual in each fiber. So it has to be a fibration functor. So this diagram would commute. So it's kind of keeping the base thing fixed. Also could be a fibration functor, so it preserves Cartesian arrows. And also could be compatible with the tangent structure in a certain way. So the tangent bundle functor induces a functor of differential bundles and also of the dual of differential bundles. We'll ask that it commute in the natural way. So we could ask for this additional structure that tangent category could have. And we're thinking of this as taking the dual in each fiber of our differential bundles. So the category of smooth manifolds has this, where you're taking the dual of each vector space. Remember, the differential bundles are vector bundles there. So if we have such structure, then we can get something we call the cotangent bundle. So if we have this D, then we can take, given the base category of this functor to its differential bundles, do this dualization operation, and now get composite functor to the dual of differential bundles. We'll think of this as assigning to each object in the base category its cotangent bundle, which is Q T star M over M. And then what it's going to do to a map in the base category, it's going to assign something which has this kind of, again, bidirectional nature, something going from T star N, pull back over N M to T star M. So given a cotangent vector on the codomain, it pulls back to a cotangent vector on the domain. And so sort of in the lens terminology, this is some way of assigning elements to the base category to dependent lenses. So what can we do if we have this structure? So just mention a few things we could do if we have this. So let's, next few slides, we'll assume we've got a tangent category with linear dualization. So now we can define what a covector field or one form is. It's going to be a map from M to the cotangent bundle, which is a section of this projection. And one of the standard things, one of the things that people like to do, have with the cotangent bundle is that covector fields can be pulled back. And this sort of just immediately comes out of the way we set things up. So if I have a map from M to N, and if I have a covector field on N, then by just essentially by the nature of what this T star does, I can pull it back to a covector field on M. So if I start with M, I'm writing here composition diagrammatic order. So first I apply F to get to N, then I apply this covector field that gets me to T star N, or I do the identity that gets me to M, then I apply this T star F, and the whole composite is giving me something from M to T star M. So starting with the covector field on M, I've pulled back to a covector field on M. Let's check out the covector field that sort of immediately follows from how everything was set up. So that's one thing we can do, sort of a nice easy thing that just follows out of how things have been set up. Earlier I mentioned that in the smooth manifolds, the cotangent bundle can be seen as an endofunctor on the étale maps. And this actually nicely comes out of the general setup as well, the general setup in terms of fibrations. So in any tangent category, we can define an étale map. So to be a map such that this diagram is a pullback. So if I start with a map from M to N, I get this naturality square, and nice characterization of asking if this is a pullback. This turns out to be the same as asking that the map be a local diffeomorphism or étale map. So this is how we can sort of phrase étale maps in tangent categories. So what does that kind of say? That says this pair is a Cartesian arrow in this fibration here. So by definition, if I apply D to it, I'd get a Cartesian arrow in the dual of the linear fibration. But it turns out that the way you construct the dual fibration, Cartesian arrows in the dual fibration correspond to Cartesian arrows in the original fibration. So if I do this whole procedure on an étale map, I can see it as giving an element of Lin of the differential bundles, not the dual of differential bundles, just differential bundles by itself. And so if I can take the top component of that, and that gives me an endofunctor from étale maps in X to étale maps in X. So just general sort of fibrational stuff, the étale maps are for which these squares are Cartesian maps in the fibration, and then sort of just from the general theory, we get this endofunctor on étale maps, which again has been sort of sometimes how the cotangent bundle functor is talked about. So the other things we can do, where I talked about this canonical flips, this kind of giving a translation between one kind of differential bundle and another kind of differential bundle. So T squared M is a differential bundle over Tm in two different ways, one with T of the projection, one with the projection on Tm. And so we get these kind of isomorphisms here, and if we apply D to that, that gives us isomorphisms between T of T star M and T star of Tm. So the tangent of the cotangent bundle and the cotangent of the tangent bundle turns to be isomorphic. That just comes out of applying D to this canonical flip thing here. This isn't I don't see this sort of isomorphism talked much about differential geometry books, but a few places kind of mention it. Another couple things that are sort of more well known about the cotangent bundle, it has a canonical vector field and a canonical covector field, the cotangent bundle. So that would be some map. The vector field would be mapped from T star M to T of T star M, and the covector field would be mapped from T star M to T star of M. And you can build these in this abstract setup as well. Just sort of comes for free by manipulating some of the existing data. So that's some geometric structures you get out of this general setup. Okay, so just lastly, so could we directly axiommatize a category equipped with a cotangent bundle? Now, why would you want to do this? So as I said at the beginning, you read some differential geometry books and I'll talk about, someplace will say the cotangent bundle is sort of more canonical than the tangent bundle. But this especially happens if you see at algebraic geometry where the cotangent things are seen as more canonical than tangent things. So maybe it's more natural to try to axiomize directly cotangent bundle as opposed to the tangent bundle. I don't yet quite see how to do that. So this is one thing we've been trying to do, but it's not clear how to do that directly yet, at least in my mind. One thing we could start off by asking a cotangent category would be a category equipped with a functor from its base category to the dual of its additive bundles. That would sort of give us some of the structure we're talking about and sort of having this pullback operation and things. But it's not quite clear yet sort of what other structure this has by itself. So for example, we saw that we get an isomorphism T star to T star T. We don't directly have an isomorphism, so kind of involution T star to T star T star. It's not clear how to
really... We'll finish in a couple minutes.
Sorry?
A couple more minutes?
A couple minutes, yeah, I'm just getting basically almost done. And it's not clear how to sort of define differential bundles in this setting as well. So just to wrap up, so if you took a tangent category with some kind of linear dualization, as I've discussed, you get an associated cotangent bundle, and the dual fibration is kind of helpful in setting this whole story up. You can get some standard results about the cotangent bundle from this abstract setup as I described. Not yet clear sort of how to define, if I wanted to directly define a cotangent category, but I think some of the structure we've been mentioning here could be helpful in doing that. I got some references here. Don't have anything like a paper yet on this general story. Is sort of still work in progress, but here's some references about tangent categories, the dual fibration, and Ben McAdams' work on relating vector bundles and differential bundles. All right, thanks everyone for your attention.
Thank you, Geoff. Let's start by thanking Geoff. And we can take a couple minutes for questions. So if you want to ask a question, just unmute yourself or raise your hand.
I can ask a silly question kind of to break the ice.
Thank you.
Just keep that in mind and don't start.
Yeah.
So you had a slide on the differential bundle in a tension category, right?
Yeah.
Where you presented this definition.
Yeah.
And then you mentioned that McAdam, I'm guessing in a different paper. Mm-hmm. So he shows that in this basic example that matches kind of the usual definition.
Yep.
So I was wondering maybe there was more of a story there. Like I'm not understanding like. So this is a definition, a new way of phrase that definition that's in that 2015 paper, and then later he shows that it matches the other one. I was wondering what the story was.
Well, yeah. So we knew that every vector bundle in the category of smooth manifolds has this structure. So every vector bundle in smooth manifolds is a differential bundle.
Okay.
And this definition seemed to be the most natural one that works in any tangent category, and particularly was kind of useful when we were trying to define connections on these kind of bundle things. It turned out this is exactly the right structure to be able to talk about connections on them. So it seemed like the most natural thing, but there was still a gap there in the sense that in smooth manifolds, was it true that every differential bundle was a vector bundle? And what wasn't not clear at all to us at the time was that a differential bundle doesn't have any kind of local triviality condition like vector bundles do, but McAdams sort of had an abstract way of viewing differential bundles that through various manipulations showed that differential bundles were the same as vector bundles, in particular also with local triviality conditions. So really sort of closed off a hole that we had. We sort of felt these are the right things and kind of hoped that they were the same as vector bundles, but didn't see a way to go to do one direction of that, and he filled in doing that direction.
Any other questions that have come up in the meantime? Matthias.
Yeah. Hi, Geoffrey. Nice talk. Thanks.
Hey, thanks.
Actually, in a work joined with Alejandro Cabrera and Enrique Bursin, we used some of these abstract isomorphisms, like the vertical lift, etc., to differentiate vector bundles over Lie groupoids and to get Lie algebras. And for us, the germinal piece of data was an action of the multiplicative monoid. What at the end of the day, what I want to say is that more general than the tangent, if this action of the multiplicative monoid is not regular, let's say, you have a higher jet bundles, like the second tangent or the third tangent, etc. And I was wondering if there is some formalization or abstract approach to these higher infinitesimal versions, like a second tangent or higher. But if you just iterate, it's not the same as taking the jet, no? And I was wondering if you know something about this formal doing what you do with the tangent, but instead of the tangent, the jet.
Yeah, that's a good question. I mean, that's sort of no is a short answer. That's something that's sort of been an area to explore, and nobody's sort of yet taken it up in a sense. So it's sort of an open question about how to define those things directly, axiomatically, jet bundles, sort of directly as we've done with the tangent bundle here. I will mention, so you mentioned Lie algebras and stuff and differentiating these vertical lifts and stuff. I want to mention Ben McAdam also has this paper on involution algebroids, which are kind of a tangent category version of Lie algebroids. And they're sort of taking some of those ideas, and working with them as well. So that might be something if you're to look at as well. But could you put a link in the chat to the paper you're talking about?
Yeah, I can. But actually, what you said is the second question I wanted to ask you. That if having this abstract approach to vector bundles, then you can talk about Lie algebras in other contexts, no? But,
Yeah. Sorry.
Okay, I will put the paper later. But thanks a lot for.
Yeah, I'll see if I can put the link about the involution algebroids, which are like sort of version of Lie algebroids. I'll put that in the chat as well.
And we have one more question from Matthias Menny.
Hello, Geoff.
Hi.
Hello, everyone. This is another basic question. It is counterintuitive for me to think of the category of rings as the category of smooth spaces.
Yeah.
So let me phrase it like this. What do you know what changes if you assume that your tangent category is extensive? I'm sure there's something else you can prove that you cannot do in the fully abstract context that you are trying.
Yeah, that's a good question. I haven't looked at that, and I don't know anybody that has. Yeah, it's a good question. I think there's lots of questions about taking a tangent category and assuming it has additional categorical structure, and then seeing how far you can push that. I was talking with, sort of related to this, talking to Bill Levere about this at some point, and he sort of said, it might be useful to consider tangent categories which, where the tangent functor has, is not necessarily representable, but still has a, which I can remember the sort of the tiny object direction, sort of a right adjoint. So I think my point is there's sort of, I think, lots of questions about taking a tangent category and adding additional categorical structure to it and seeing how far that takes you. So extensive is something I hadn't thought about at all, but that's one possibility, yeah.
I think let's keep the rest of the questions and discussion for the forum. And also, if people have further papers related and so on, you can put them in the chat, but it might also be useful to put them in the forum because then others can see them later too if they join in. They weren't here perhaps. So let's thank Geoff one more time.
Thanks.
And our next speaker will be Andre Jorial. Andre, when you can share your screen.